And light does the same thing. Relative to you, it always travels at the light speed. You get it? So regardless of your motion, the light travels at the light speed. That's it. All right. So according to the second conclusion, light is going to be able to reach the mirror because the light always travels at the light speed relative to you, regardless of your motion. Got it? Physics allows two conclusions. So the question is, which conclusion is the most accurate one? All right, so here's what happened, guys. You end up committing to something that's going to get you into trouble. It's important. Imagine that this thing is moving at 120 miles per hour. All right, so this is the speed of the ball, and this is the speed of the vehicle that you're in. And I'm going to place some kind of a stationary observer on the outside. This is your stationary observer. And somehow imagine that stationary observer is able to see through materials because this is a space alien. So the question is, how fast is this ball moving with respect to the space alien? Inside this vehicle, which is traveling 120 miles per hour. All right, guys, so what is the speed of this ball with respect to the space alien? What do you do?
180.
You end up adding up these speeds, right? All right, so give yourself 5 points for that one. So you end up adding up these speeds. So this is going to give you 180 miles per hour. All right, so let's try play the same thing. All right, so here's light moving. Here's light moving relative to Einstein at the light speed.
So does light travel through a medium?
Hold on. So here's the speed. All right, so here's the speed of light. All right, so here's the speed of light. Light is moving at the light speed relative to Einstein, and Einstein is in a reference frame, which is moving at the light speed. So how fast is this light moving? How fast is this moving relative to space alien outside? So what do? You add up the speeds one more time using the same formula. This time you end up getting C plus C, so it's going to be 2 times C. Shit. Okay, what happened? All of a sudden, logic broke down. All right, so ball is moving at 60 miles per hour relative to you in a vehicle which is moving 120 miles per hour relative to the space alien. So the ball is moving at 180 miles per hour relative to the space alien. That makes sense. So the light is moving at the light speed relative to Einstein, as Einstein is moving at the light speed relative to the space alien. So what that means is this light has to move at double the light speed relative to the space alien, and boom, everything broke down. We end up reaching an impasse, guys, at this moment. All right, so where do you go with this? All right, this little thing took 10 years to figure out. All right, Einstein asked the question at the age of 16, and all of a sudden he's thinking, wait a minute. If everybody experiences the same light speed, regardless of their motion, and when the light is moving at the light speed relative to Einstein, if Einstein is also moving at the light speed relative to the space alien, this light has to move double the light speed relative to the space alien. It does not make sense. So what do? Well, guys, here's the difference between Einstein and the rest of us. This guy's a genius. We are not so much. Einstein says, screw this. He says the mathematics, he says the sort of math is no good. It says, let's make an assumption that everyone experiences the same light speed. What that means is you're moving at the light speed, the light moves at the light speed relative to you, and the same light is going to move at the light speed relative to the space alien. It says, let's make that assumption and then proceed from there. And then what happens? All right, so he comes up with 2 postulates. The first one is known as the relativity postulate, which means that you're moving in a straight line at a constant speed, except now you're moving near the light speed. This is known as an inertial reference frame, straight line at a constant speed. The second one is known as the speed of light postulate, which means that everyone experiences the same light speed regardless of their motion. That's what it means. All right, so before we proceed, let me ask you this question. And this question is important to your understanding of the concept. What's the meaning of a postulate? When somebody says, I'm postulating something, what does it mean to you? If somebody says, I'm postulating something, does that mean that person is constipated? All right, so if you don't have the right understanding of the concept, because this is the sort of stuff that I noticed that we're struggling with this COVID thing. And a lot of people don't understand science because science is kind of messy, all right? When somebody says postulate, what does it mean? Because the postulate means assumption, all right? These are not scientific facts. Einstein is saying, I'm making assumptions. I'm going to build a theory based upon these assumptions, all right? And then I will test the prediction set. So postulate means an assumption. When somebody says, let's postulate something, all of a sudden you pay attention. Oh, this guy's about to do something weird, all right? Because postulate, the term itself has gravitas. When somebody says, let's assume something, you go, let's not. All right, so this is an assumption. So speed of light postulate is a speed of light assumption. What is the assumption? Assumption is even if you're traveling at the light speed, you still see your reflection in the mirror because light still travels at the light speed relative to you. That's what it means. Got it? That's an assumption. That's not a scientific fact. That's an assumption. And he's going to build a theory based upon these assumptions. There are two assumptions. Number one, you're moving near the light speed in a straight line at a constant speed. All right, so that's one assumption, underlying assumption. The second one is regardless of your speed, light speed remains constant. All right, so everyone experiences the same speed for light relative to, regardless of their motion. That's what it means. So having said that, if I'm traveling my Suta Ford Tempo at the light speed, if I were to turn on the headlights, would I be able to see what's in front of my Ford Tempo? The answer to that question is absolutely yes, provided that this assumption is correct, right? If this postulate is correct. All right, so whenever you guys are ready, just jump in.
D.
All right, very good. I mean, you got two spaceships traveling at half the light speed, one towards the sun, the other away from the sun, and they're trying to measure the light speed in both spaceships. All right, so, and they will measure the light speed exactly to be C, right? All right, so the light speed is going to be independent of the motion of their reference. So D is the best answer. So those of you guys who picked D, give yourselves 5 points. Those of you guys who said D, give yourselves 5 points. Those of you guys who picked D, give yourselves 2. Go take a break for 10. And I'll see you guys in about 10 minutes. Okay, but check to see if this is okay. Let's get moving.
Hold on, we're taking off.
Fortunately, this phenomenon is only noticeable close to the speed of light. Imagine yourself alongside early 20th century science fiction swashbuckler.
All right, so everybody's going to experience the same light speed, according to Einstein. If everybody experiences the same light speed, so if that's the case, here's what the question is. What happens to space and what happens to time? All right, so as your speed starts to approach the light speed, distance over time. Imagine that you're traveling at the light speed from here to New York City. How much of the lightscape are you going to be able to experience? Almost none. Space is going to contract. All right, so space divided by time still should give you the light speed. So what happens to time? Time's going to slow down. Immediately, we will have two predictions. If everybody experiences the same speed for light, what happens to you when you start to approach the light speed? Two things will happen. Space is going to contract in the direction of motion, which is known as contraction of space. And the time is going to slow down, which is known as the dilation of time. So the time is going to slow down for an object traveling near the light speed.
Flash Gordon. When not fighting the bad guys or trying to escape from some monster, you're dashing around the galaxy at incredible speeds. While you are, your clock and those back on Earth are running at different speeds. Assuming you've been gone for the better part of a year, when you get back, everyone you knew would have been dead thousands of years. It's the ultimate example of relative time.
Faster you go, more the time is going to slow down for you.
8, 7, we are go for start. 5, 4, 3, 2, 1. Booster ignition and liftoff of Atlantis on a mission to study planet Earth.
Astronauts travel 30 times faster than corporate jet pilots. Joe Tanner traveled 4.5 million miles when he flew in a shuttle mission in 1994. Joe has an identical twin brother, David.
After the space flight, now I am 321 microseconds younger than I was before the space flight. I guess I don't feel all that much different. I used to have a mustache like yours, but everyone says I look so much younger without it. I shaved it off so I could catch up on those 321 microseconds.
Joe and David are now living examples of what physicists call the twin paradox, a result of time dilation. The question of why time slows down for one traveler as he approaches the speed of light, but not for the twin who stay behind. As fast as the shuttle is going in orbit, it's only going a tiny fraction of the speed of light. That's why Joe is only
321 microsecond difference. 321 millionth of a second difference. So who's going to be 321 millionth of a second younger? The one traveling in space. Einstein's theory would have given us the same number, dilation of time. There are two different times at work here. Now imagine that you're moving at a given speed relative to the speed of light. All right, and t is known as the relativistic time. And in this case, t naught is known as, I'm going to call this the rest time. All right, so relativistic time is, the rest time is going to be measured by an object moving near the light speed. And this is the speed that we measure here on Earth. This is the Earth reference frame that we will get to use relativistic time. So we got two different speeds. They're not the same. We got two different times. They're not the same. Okay, so let's demonstrate the concept mathematically. Number one, the time difference between the twins is relatively small. They were using atomic clocks. They were initially synchronized. One of them obviously kept here on Earth. The other one was in space for about a week, moving about the Earth, roughly about 17,500 miles per hour. Upon return, they noticed that they were no longer synchronized. The one in space was actually lagging behind by 321 microseconds. And the reason why that happened is because when you're traveling at 17,500 miles per hour, you're moving at a very small fraction of the light speed. So if you were to spend 10 years in space, upon return, everyone would be 10 years older, including yourself, including your twin. But if you were to travel at 90% of the light speed for the next 10 years, you would age 10 years, but upon return, you would notice that your earthbound twin would be about 23 years. It would have been 23 years for him, which means he would be 13 years older than you. If you were to spend 10 years in space at 95% of the light speed, upon return, you would notice that it would be 32 years here on Earth. So your twin would be about 22 years older. At 99% of the light speed, if you were to spend 10 years in space, upon return, you would discover that it would be 70, 71 years here on Earth. If your twin is still alive, obviously it's going to be 61 years older than you. At 99.9% of the light speed within 10 years, you can leap 223 years into the future. At 99.99% of the light speed within 10 years, you can leap 700 years into the future. At 99.999% of the light speed within 10 years, you can leap over 2,000 years into the future. If we had this technology, imagine, guys, about 2,000 years ago, you would be arriving just about, if you missed the main event, you would be arriving just about now to catch the main event in the movie form. And I'm talking about crucifixion. Evidently, it's, according to the moviegoers, it's just as bad as the real event was. It's just as gruesome, except a little bit more entertaining because of the background music. So faster you go, closer you get to the light speed, the more the time is going to slow down for you. All right, so notice that you start to, the closer you get to the light speed, within 10 years, you can almost travel years into the future.
C.
C is the best answer, so give yourself 5 points. Those are the best. Give yourself 2. All right, sooner or later, we will run out of resources here on Earth. Our best bet is to colonize the universe, obviously. So we are looking for Earth-like planets. And we keep discovering Earth-like planets all over the universe. The nearest one, which was discovered about 7 or 8 years ago, they called it the super Earth, super-sized Earth, except it was located like 800 light years away. All right. If we had the technology to travel there at the light speed, how long would it take for us to actually travel there? And how many people will volunteer for something like this?
Wouldn't it still take like 800 years?
All right, so that sounds like a problem, right? Okay, so it doesn't sound like you're ever going to be able to get there within your own lifetime. So a lot of people would say, okay, I'll wait for the next one. All right, if we can find something closer, we'll go to that one. 800 years is, at the light speed, it would take 800 years, right? That's what most of you guys are thinking. All right, so think back, guys. What happens to your time when you start to approach the light speed? It slows down, right? What happens to the time when you reach the light speed? It stops. So if we had the technology to travel at the light speed to a planet which is located 800 light years away, how long would it take for you to get there at the light speed?
Depends on who you ask.
It would take no time at all, right? So how long would it take? It would take no time at all. You're here.
You're on the ship.
Yeah, if you're here, you're there. It would take no time at all at the light speed. So you get there, look around. People, there are creatures there who look like fish, intelligent creatures. Except, you know what? You don't like fish, right? So you say, screw this. I'm just going to go back home. So you travel back home at the light speed. How long would that take? It would still take no time at all. Except the round trip, from our perspective, would take 1,600 years. By the time you get back here, it will be 1,600 years in the future. And guess what? Thanks to evolution, people here start to look like fish too. So now you can never go home. So that's what happens. All right. So from your perspective, it's going to take no time at all. From our perspective, the round trip is going to take 1,600 years.